All right.
Okay, awesome. Thanks, guys, for coming. It is my pleasure to introduce to you Associate Professor from Williams College. That is correct?
Yep.
Okay, great. Steve Miller. He is in the Department of Math and Statistics. He has his PhD from Princeton, an MA from Princeton, and a BS from Yale. So he definitely knows what he's talking about when he's talking about.
And I grew up in Cape Cod, so I know coastlines.
There we go. He's going to be talking to us today about complex dynamics and
from sea to shining sea, complex dynamics from combinatorics to coastlines.
That.
So, thank you.
With that, I will let you get started.
Hi. So, it is great to be here. It's been a while since I've been to Mystic. I actually grew up outside of the Boston area, so I've come down here and other places like this when I was growing up. My kids are exploring the area right now. They already heard this talk in the car, and they've already given me comments. So you're going to get a better version of the talk. This is not a typo. This is how mathematicians draw the C standing for the complex numbers. And so what I want to do today is I want to show how mathematics can help you with some of the problems you might be studying, as well as how mathematics is not able to help you, so that you can be a little bit aware of what you can do and what the limitations are. If you have any questions as I'm going through this, please just raise your hand, speak up, throw something at me. This is meant to be interactive, and I will try to resist the temptation to do too much mathematics and algebraic calculations. So apologies if you want to see more. If you do, just ask me afterwards. Okay, introduction. So I want to talk a little bit about the turbulent 60s. This is a little bit before I was born, so I've had to read up about this. Two extremely influential papers came out. One was by Lorentz. Out of curiosity, how many of you have read this on deterministic non-periodic flow, or at least heard of this? Okay, good. This is a paper you should be aware of. The other one is more of a math paper, although normally we don't have such fun titles. How long is the coast of Britain? Okay, this is not, I've got a bunch of grad students, I'm going to give them some rulers and have them walk around the coastline and measure things. How could we actually mathematically handle a question such as, what is the coastline? So the question is, why these two papers? What do they have in common? So here's the conclusion. This is always the difficult part when you're giving a talk. Do you just read the conclusion? Do you pause while people are looking at it? Just briefly summarizing, from the Lorentz paper, it basically says all solutions are found to be unstable. And then there's a little bit more, but essentially when we're trying to predict weather and we're trying to calculate models for weather, we need to solve the equations. And we want to see, based on our initial observations, can we predict what the weather will be in the future? And this is saying no, that the equations that govern the climate are too complex to be able to solve exactly with the abilities we have to make measurements. The other paper from Mandelbrot is basically when we try to consider things such as what is the coastline of Britain, we actually get an infinite answer. That the length of the British coastline is infinity. So what does this really mean? Why do we care about something like this? It means that dimension is a little bit more complicated than you're used to. So in a moment, we will go through what is dimension. We'll do the common sense one that I can do with my kids in the car, and then we'll do the one that mathematicians use so that we can actually get real salaries. We end up seeing stuff like the dimension of Britain's coastline is 1.25. Germany, the land frontier in 1899 was 1.15. Spain, Portugal, the land boundary 1.14. Australia 1.13. South Africa actually does a really good job. Their dimension comes in around 1.02. That's close enough to be almost experimental error. When you think of dimensions of subjects, you don't think of something like 1.25. And so I want to explain a little bit where this comes from and why we should care about this. So what is the link between these two papers? The link is extreme sensitivity to initial conditions. How many of you have heard of the butterfly effect? If a butterfly flaps its wings in Tokyo, it can cause a tornado someplace a week later. The best response I've ever heard is, we've got to find this butterfly. And so the consequence of this is that if we need to know everything to 30 decimal places in order to accurately predict what's going to happen in a short amount of time, we might as well give up. We cannot make measurements that accurately. And so there are incredible consequences in terms of what we can do with the mathematics. Okay, so let's talk a little bit about dimension. So does anybody want to define dimension? It does not have to be the mathematical dimension. Just how would you define dimension to an 8 or 10-year-old. And if necessary, I can call them and bring them down. Anybody want to take a stab? How do you try to define dimension? Or give me, okay, yes.
Like the parameters of the space.
Okay. So can you give me, what are the possible values for dimension? When you think of dimension, the dimension could be what?
I'm thinking like volume.
Okay, so what dimension would a volume be? So if we had a sphere which has volume, this would be?
Isn't it like something cubed?
It's something cubed, so how many dimensions would a sphere be?
3.
Would be 3, right? You can specify where you are with 3 different parameters. You can do it as the distance from the center, you can do it as, and then 2 angles. Or you can do it as the x, y, z. So a sphere would be a nice 3-dimensional object. All right? What other kinds of dimensions could we have? Instead of a 3-dimensional object, we could have a 2-dimensional. The surface of this table. This is where you get your Euclidean geometry. Or you could do the surface of a sphere, which would be a nice 2-dimensional object. Locally, it's going to look flat, but if you go on a large enough region, you should hopefully see that the Earth is curved. Okay. What else? We've got 3 dimensions, 2 dimensions. What dimension? Like the coastline, or a line segment, or a curve. Okay. So here's the mathematical way of defining dimension. Take some set of n tuples of real numbers. And that's our set. Yes, we do this. If dilating S by a factor of R yields C copies of S, so that means if I rescale every direction by a factor of R, this is the Boston area, so I can talk like this. If I get C copies of S, then the dimension D satisfies R to the D equals C. All right, let's put this in practice. Here's a unit segment. I'm going to dilate it. I'm going to expand it by a factor of 3. How many copies of it do I have? 3. So I want to solve the equation, and I should be able to use my laser pointer, R to the D equals C. So since R equals 3 and C equals 3, D must equal 1. And so this is a nice mathematical way of saying this is a 1-dimensional object. Okay, not too bad. Let's go on to 2 dimensions. I take a square 1 by 1. I dilate each direction by a factor of 3. And now how many copies of the original square do I have? 9. And so I need to solve the equation R to the D equals 3. So 3 to the D equals 9. So I get D equals 2. Okay. I was having a little trouble having a 3-dimensional thing project from here. I guess you don't have quite the same technology we have at Williams. So we will skip doing the sphere and stuff like that. You should come up and visit us in the Berkshires. All right. How many of you have seen the Cantor set? Good. So this is a chance to show you that dimension is a little bit more interesting than you might expect. So what I'm going to do is I'm going to take a unit line segment. It should really have no thickness, but in the interest of some people whose eyesight may not be so good, I'm going to draw it a little thick. And I'm going to chop out the middle third. And I'll be left with 2 segments. And then for each one of them, what do you think I'm going to do? Chop off the middle third. And now what? Chop off the middle third. And now? Keep chopping, keep chopping, keep chopping. Okay, 1, 2, 3, 4. Okay, so if you have really good eyesight, you can see there's a little gap between some of the stuff here. Okay? You need really good eyesight at this point. My kids could not see this in the car. What do you think the dimension of this set is? So one of the things I like to tell my students is, if you can't answer the question exactly, can you give me some upper bounds and lower bounds? Can you give me an upper bound for the dimension of this set? It shouldn't be greater than what? So, again, yeah, it shouldn't be greater than 1. It's a subset of the line. The line has dimension 1. I shouldn't have a subset of a line all of a sudden being an area or a volume. So I agree that it should be no more than 1. Can you give me a lower bound? Greater than 0. Yeah. This is not a negative dimension, right? No matter how bad a team is, they don't have a negative chance of winning the game. You're not going to have a dimension below 0. It's somewhere between 0 and 1. So the question is it exactly 0? If it was just a point, it would be 0 dimensions. I have infinitely many points. If it was a solid line, it would be dimension 1. Well, let's play our game. We want to look at how many copies of it would we get if we dilate it by a factor. So let's dilate it by a factor of 3. So if I take this and I expand it by a factor of 3, this piece here would come up to the whole thing here. So these 2 pieces here would expand to those 2. So these ones would expand to those 4. So if I dilate it by a factor of 3, I end up having how many copies? So if I took just this part over here, how many copies would I get? Not 6. I start off with this part over here, and if I dilate it by a factor of 3, how many copies do I have if I call this part here the original?
3.
Not 3. I think I finally heard the answer.
4.
Not 4.
8.
Not 8. We're running out of numbers. 2. Right? This part here became this whole thing over here. These 2 parts here became this and this. These parts here became this, this, and this. From this one part here, I'm basically getting 2 copies. So think of this as, this whole thing down here is 1 copy in the limit, and this copy over here is another one in the limit. So if I double it, if I triple it, I get back 2 copies. So I now need to solve 3 to the d equals c. So 3 to the d equals 2. So I take logs. D is the log of 2 base 3, or about 0.63. So we actually have an object whose dimension is fractional. It's greater than 0, and it's less than 1. Now, mathematicians can study, and we do almost anything. The question is, when are we studying something that's worth looking at, especially for the stuff you guys are all interested in? So the goal is to try to connect this to things you might have been looking at. Let's do another example. All right, how many of you have seen Pascal's Triangle? Okay, how many of you were traumatized? Okay, yeah, a few hands are still up. So the rule is pretty nice. You have ones going on the outside, and every number inside is the sum of the number to the up to the left and up to the right. So 10 is 4 plus 6, 15 is 10 plus 5, 7 is 6 plus 1. Okay? I want to play a game on Pascal's Triangle. And the game is as follows. I'm going to put a dot if it's an odd number, and I'm going to delete it if it's even. So in the interest of space, we actually say, if we're in the nth row and the kth object, we just denote that by n choose k. So 4 choose 3 would be the element, so we start counting with 0 because we're mathematicians, go 0, 1, 2, 3. So 4 choose 3 would be the 4th element in the 4th row. Computer scientists also count like this. Okay. So if we just had a Pascal triangle with 1 row, we would have 1 dot. It would just be the number 1, so we would have a dot. If we had 4 rows, it goes 1, 1, 1, 1, 2, 1, so we remove the 2, and then 1, 3, 3, 1. So if all we do is we replace odd numbers with dots and delete even numbers, we've only deleted 1 even number. Sometimes instead of saying, looking at things, what's the remainder when we divide by 2, we sometimes use the word modulo. And so we say 15 mod 12 or modulo 12 is what's the remainder when we divide 15 by 12. So if I told you it was 10 o'clock a few hours ago, it's 5 hours later. What time is it now? 3. So you've just said 10 plus 5 is 3, right? Does this mean the program here is admitting people with really bad math skills? And I've been called by William secretly to fix this. That we have to convince you that 10 plus 5 does not equal 3, it's actually 15. No. 10 plus 5 is 15, but on a clock, you can't tell the difference between 15 and 3. And so when we say 15 mod 12, the remainder is 3, so it's really the same. So I could say, I'm looking at just, is it odd or even, or I'm looking at what is it mod 2. The reason is we might want to do things other than mod 2 later, so it's good to just introduce some terminology. Let's go a little bit further. This is now Pascal's triangle with 8 rows. Does anybody notice a pattern? I'm sorry?
Said it's a bunch of little triangles.
It's a bunch of little triangles. Do they look like the same little triangles? So we've got this little triangle here, then it's repeated here and here, and then this whole block is repeated here and here. And so I couldn't find a good movie for this on the web, so I wrote this a few years ago. Let's hope it works. So what I'm going to do now, it is so. All right. So what I'm going to do now is I'm going to play a little movie. And what I'm going to do is I'm going to start drawing more and more rows of Pascal's triangle. But what I'm going to do is rather than putting in the numbers, I'm going to put in a dot if it's odd and leave it blank if it's even. Okay? because of the way the program is, it's actually easier for me to draw Pascal's triangle not coming down from the top, but coming from the right. If this bothers you, just take a little nap right now and put your head down, and it will look like the normal way. Okay? The other thing is, as I get more and more rows, I'm going to need a bigger screen. So you got my email about the screen extension? Okay.
Sorry about that.
Okay. So.
There's a whiteboard right there, though.
Yeah. Okay, so fortunately there's a switch I have in my program. I will just activate that. And what I will do is I will always compress. So no matter how many rows I have, I will always print it in the same size box. Okay? And let's see what happens as we run it. All right, so it jumped a little bit too fast. Let me try to pause it and do it again. Okay, there we go. And so hopefully you can see the structure emerging as it goes further and further down. And you can hopefully see you're getting more and more copies of the same thing. So it's a fun challenge as to what's the most efficient way to code this. At some point, the resolution is such that we really can't tell the difference anymore. All right, I will stop that here. I will try to stop it here. It's just having so much fun printing it out. Okay. So here's just a screenshot of 3 little places. This was small number of dots, more and more. And you can begin to see a pattern. Does anybody notice anything similar to this and the Cantor interval set we just did a moment ago? There's a common theme as to how they're constructed. Any thoughts? What does it look like we're removing? Yeah, but instead of now being an interval, it looks like it's a triangle. So if we start off with a full triangle, let's remove the middle triangle. And now we'll have 3 triangles. From each of these triangles, we remove the middle third, the middle triangle. And now we should have 9 triangles. And we keep doing this. Doesn't that look a lot like this, except just rotated?
Yeah.
And so this is called the Sierpinski Triangle. And we can ask the same question, what's its dimension? So can somebody give me an upper bound for what the dimension should be? It should be no more than 2. Good. Why is it no more than 2?
Because the original full triangle.
Yeah, it lives inside a full triangle. This would be the same as, you had $1,000 in the bank, somebody withdrew some amount of money, and you ended up with $1,200. You're not going to have more money than you start with if somebody's pulling things out. Can you give me a lower bound for the dimension? It's got to be at least 1. We've got whole sides over here. So we should have a dimension somewhere between 1 and 2. So we could play the same game. If I took this part over here, if I double all the dimensions, this side expands out to this whole side, this side expands to this whole side, this side is pushed out to here. So if I double this part in here, how many copies of this do I now have? I get 2 more pieces, so the total number of copies would be 3. So when I try to use my formula, r to the d equals c, if I double, if I equals 2, c equals 3, so I want to solve, and I get 2 to the d equals 3, so the dimension is the log of 3 base 2, or about 1.58. So the dimension does sit between 1 and 2, as you would expect. Okay, so there are other ways you could generalize. And so one way we could generalize is we could look at things mod 3, mod 4, mod 5, and you can ask about the different structures you have here. I was about to say, normally it was a nice red light, but okay, that must be because it was just displaying so much red in the beginning. Okay. So what are the connections between this and the coastlines? So there was a really nice coastline paradox. They were trying to measure the length of a coastline, and the value they got changed with the scale of the measurement. So if you used a long rod, and you have to put the rod down, and then you pick it up, and you put it down again, then you pick it up and you put it down, that's doing something like this. Which do you think will be more accurate, having 1 long rod or 2 shorter rods? Okay. Is there any way the 2 shorter rods could be less accurate? Okay, how?
If the coastline was straight.
But if the coastline was straight, couldn't we just put those two shorter rods together and make the one longer
Yeah,
rod?
but it wouldn't be accurate because your rods don't connect completely.
So I have friends who are physicists or economists, and they can give me these idealized perfect objects.
We don't have that in the real world.
So this is an interesting question as the difference between the real world and the theorist's world. In the theorist's world, you can't do worse because you could always put the two short ones together and make the long one, without any error. Just hold them together, have them perfectly fitting. And that as you take more and more, you might not do better, but you shouldn't do worse. And so as you take more and more, you have the ability of seeing more of the shape of the coastline. That if you're using a really big rod, I can't capture all of this. And so, for instance, here are some pictures of Great Britain. Here is using a 200 kilometer, 100 kilometer, and a 50 kilometer. And when you do this, the size of the coastline goes from about 2,400 kilometers to 2,800 to 3,400. And if you keep taking smaller and smaller rods, it turns out that the number diverges and goes off to infinity. Which seems a little bit absurd to have an infinite size for the coastline of Britain. So what's going on here? So hopefully this is not too blurry. It's fine on my screen, but it does seem to have little issues here. This is called the Koch snowflake. So what I'm going to do is I'm going to take a straight line. And you know how before I threw away the middle third? But rather than throwing away things, let me add stuff. So I'm going to put an equilateral triangle right at the middle third, and I'm going to just drop the bottom of the equilateral triangle. So I'm basically replacing a segment over here with two segments of the same length coming up. Has the length increased or decreased? I'm sorry? Increased. So if this was 3 units long, how long is this? 4. So the length of this is 4/3 times the length of that. Now I play the same game. I take each segment and I throw away the middle third and I put equilateral triangles. This segment, I've increased its length by a factor of 4/3, by 4/3, by 4/3, by 4/3. So the whole thing has length 4/3 times the previous. So if this length was 3, this length is 4. Now I have to multiply by 4/3. Now it's 16/3. The math is getting painful for me because I can't divide. What will happen as we keep doing more and more levels? What will the length go to? The length will go to infinity. And it'll start to get really, really jagged, and it will reach a point where you can no longer see the difference. Does everyone agree that the dimension of this should be less than 2? It's contained inside a nice square. It shouldn't be more than 2 dimensions. The dimension should be at least 1 because it's like a line or a curve. So when you do the analysis, you actually get the dimension is about 1.26. Because if I took something like this and I multiplied by 3, I would get 4 copies. 1 copy, 2 copies, 3 copies, 4 copies. So 3 to the d equals 4, so d is the log of 4 base 3. So you get a dimension of 1.26. And I said earlier that the coastline of Britain was about 1.25. So the dimension of Britain is actually very similar in terms of structure to something like this. Okay, what I want to do for the last part of the talk is talk about chaos. Okay, so much of math is about solving equations. So I will try to remind you of some equations, some of the great all-time classics that you studied years ago. Polynomials, ax plus b equals 0. The root is negative b over a. Does this sound good? Next one, what's this called? What formula? Quadratic formula, excellent. Negative b plus or minus square root b squared minus 4ac all over 2a. There is a formula for the cubic, there is a formula for the quartic, and there's no formula for anything higher. This doesn't mean they don't have roots. A polynomial of degree 5 has 5 roots. A polynomial of degree 6 has 6 roots. It means we don't have an explicit formula for them in terms of the coefficients. This is beautiful to have something like this. If I know this is modeling something, and then I find out, oh, actually the value of b is 10% too small. Well, this tells me exactly how my roots change. If you can solve something in terms of the parameters of interest, this is gold. The fact that I can't write down the solutions to these general equations in terms of my parameters is painful. It means we have to use numerical techniques. So I'll teach you numerical analysis in the next 10 minutes. Okay, not a big deal. Now, how many of you have ever seen the formula for the cubic? The story I heard, and this goes back a couple of hundred years, is that mathematicians could challenge each other for jobs. I have not investigated to see if the story is correct or not, because I like the story. And if you could challenge someone and they can't do your challenge, but you can do theirs, you get their position. So someone came up with the formula to solve the cubic and kept it in strategic reserve. So that whenever somebody challenged him, he would just say, solve those 10 equations. And if you don't have the formula for the cubic, you can't do it. Why? Well, here are these 3 roots for the cubic. Okay? Negative b over 3a minus, and about this point my kid said, that's enough, Dad. Okay? And it goes over multiple lines. So these are the 3 different roots for the cubic. I know you're dying to see the quartic. This is the first of the 4 roots to the quartic. I had to shrink it down to this level. Hopefully it's not visible really, and that's the whole point. But it's an explicit formula. If you tell me what happens to A, I can tell you how things vary. We don't have anything like this for higher. All right, so I want to teach you the method divide and conquer. It's one of the oldest methods we have. It's extremely powerful. Imagine you have a continuous function. Can anybody say what a continuous function means? Yes.
It doesn't have any gaps or.
Good.
Yeah.
Yes. When I'm collecting my salary as a math professor, I need to do something with epsilons and deltas and whatnot, but when I'm in public, there's no gaps. If you draw it with a pencil, your pencil doesn't leave the paper. You don't assign 2 values to the same point. So imagine I have a function and I tell you it's negative around 0, it's positive around 1, and it's continuous. Can you tell me anything about what must be going on in between? Yes? It must pass the line. There's no way a continuous function can stay negative the whole time and then jump up to here. This is actually one of the most powerful observations we have in mathematics, because there has to be a root now for this function. So how are we going to find the root? Let's look at the value in the middle. If we're really lucky, the function is 0 and we're done. If not, it's positive or it's negative. Let's say it was negative at a half. Where must the root be? Yeah, it must be in the second half. And if it was positive, where must it be? In the first half. Now note, it's possible the function could go up, down, up. There could be multiple roots. All I know is there is at least 1 root. All right? So this is just the math speak as to how we do this. Assume f is continuous, f of a is less than 0 is less than f of b, that f has a root between a and b. To find, look at the sign of f at the midpoint. If the sign is positive, look between the midpoint and b. If it's negative, look between a and a plus b over 2. Lather, rinse, repeat. This is the shampoo instructions. Right? In case you've never looked at the directions as to how to use shampoo. If you would have followed the directions for shampoo, technically what would you do for the rest of your life? Wash your hand. Technically, that is all you would do for the rest of your life. This is probably why most people don't read the directions to shampoo. But mathematically, it's a really good strategy. Keep doing it and keep iterating it. Every time you iterate, you get a little bit better. So for example, let's say f of 0 was negative 1, f of 1 was 3, we would look at f of a half. If f of half is a 2, then we know that there's a root between negative 1 and 2, and so on. So what I did here is I chose one of my favorite numbers, the square root of 3. So in case you don't remember, the square root of 3 is about 1.732050807 ... And I just applied this method. So here is the choice, my first choice, my second choice, my third choice, my left endpoint, my right endpoint, the value of my function at the left, the value of my function at the right, the error, square root of 3 minus the left, square root of 3 minus the right. And so I'm looking at the function x squared minus 3, and I'm trying to find which x solves this. And what x solves x squared minus 3 equals 0? So if I want to solve x squared minus 3 equals 0, what's the root? Square root of 3. Okay? And so you see if I plug in 1 and 2, f of 1 is going to be 1 squared minus 3. It's going to be negative 2. If I plug in 2, I'll get 2 squared minus 3, which is 1, which is positive. So I see because this is negative and this is positive, there's got to be a root between there. So now I'll look at f of a half. F of a half turns out to be negative, so the root will be between negative a half and 2. and I keep marching down, and I do it 10 times, or better yet, you might be able to guess what program this is. Have Excel do it 10 times. And I get, after 10 iterations, the square root of 3 is somewhere between 1.7304 and 1.7324. And the correct answer is 1.73205. So I'm not too bad. I'm getting almost 3 digits. So whenever you do something, you want to know, how good is this? How much work am I doing, and how much gain am I getting? So if you count by powers of 2, so who here knows computers? Anybody know computers? All right. There are not, how many people know Latin and Greek? All right. I always get the two languages mixed. How many megabytes should there be in a gigabyte if we're using these prefixes correctly?
I think that's Greek and I speak Latin.
Good answer. So mega to giga should be a factor of 1,000. Okay? But in computer science, yes?
1024.
In computer science, it's 1,024. The reason is computers work in base 2. On, off, yes, no, Red Sox, Yankees, binary splits in life. And so 1,024 is 2 to the 10 is almost 1,000. So for the computer scientists, it's close enough to those prefixes. Let's just go megabyte, gigabyte, and not introduce a new terminology. But there's technically 1,024 megabytes in a gigabyte. What this means for us is every time we do this divide and conquer, we have our uncertainty. So if we do it 10 times, our uncertainty is reduced by a factor of 1 over 1,000, or we get about 3 decimal digits. Do it another 10 times, and you get another 3 decimal digits. Do it another 10 times, you get another 3 decimal digits. So if I want 6 digits, I do it 20 times. 9 digits, I do it 12 times. I've lost, no, I'm sorry. 3 digits is 10 times, 6 digits is 20 times, 9 digits is 30 times. I'm going to show you a new method called divide and conquer. A new method called Newton's method, which is much better than divide and conquer. The way it works is we use calculus. So all I need for divide and conquer is that my function's continuous. How many of you have taken calculus at some point in your lives? Okay, there should be a reason why we had you do this, right? It's not just because we want jobs. It's not just because they did this to us when we were little. We're going to do it to you. You should be able to get something out of these calculus courses. The big concept in calculus is you take a complicated function and you replace it with something simple. The simplest function we can think of is a straight line. So the idea is we're going to find a straight line approximation. And so this is just going through the math. The slides will be online if anybody wants to see. Informally, this is what we do. Here's our curve, x squared minus 3. So here's the square root of 3. I take some point, and this will be my initial guess for the square root of 3. And I look and see, am I right? Nope, not even close. Okay, what I'm going to do is I'm going to use calculus, and I'm going to draw the tangent line to the curve at this point. So the slope will be the derivative of the function at that point. And what I'm going to do is I'm going to make a bad assumption. I'm going to say my curve that I care about is perfectly the straight line. That's wrong. But let's see what it gets us. So we replace our curve with a straight line, and we see where that straight line hits the x-axis. And that will be our next guess for the square root of 3. And then what we can do is we do the shampoo method, lather, rinse, repeat. We see where are we on the curve, we draw the tangent line, and we see where we hit. We do this again and again and again. And the reason this does spectacularly better than divide and conquer is we use calculus. All we use for divide and conquer is that the function is continuous. By using calculus, we can do a lot more. How much more? Well, after we do the algebra, we not only have a better approach, we have an explicit formula. The next guess, the n plus first guess, is 1/2 of your previous guess plus 3 over your previous guess. Imagine you guessed the square root of 3. Then I would have square root of 3 plus 3 divided by square root of 3. Well, 3 divided by the square root of 3 is the square root of 3. 3 plus square root of 3 is twice square root of 3. Divided by 2 is square root of 3. Good. If we have the right answer, we stay at the right answer. If we have anything else, we start converging to the right answer. We start converging to the square root of 3 very rapidly. How rapidly? I had it print out the first 3 ones over here, And then just for fun, I printed out the fifth one. You get a rational approximation. So it says the fifth approximation to the square root of 3 is this number divided by this number. And if you want to look at how many digits of accuracy we get, down here in bold, around the 34th digit is where we first noticed a difference. This was the problem when I was an undergraduate that moved me from physics to math. To just see in 5 simple guesses, I'm getting 34 digits. If I did one more guess, I would have over 60 digits correct. You double the number of digits correct every single time. So the more times you do it, the more accurate it is. And you have it as a nice fraction, which computers love to work with fractions. It's an incredibly powerful method. And just to see how far down you have to go. So it may not be 34. We were trying to count this in the car. There was a lot of construction. It was a little bumpy. Our finger might have moved a little bit. But on the order of 30 digits right with just 5 simple steps. All right, let's play a game. I'm going to start off with an easier polynomial. I know it's really not that hard to find the roots of x squared minus 1 equals 0. All right, I just want to choose 2 things where we all know and agree that the numbers are 1 and -1. And so here is my formula to calculate. So I take a guess, and I keep iterating. So here is the root at 1. Here is the root at -1. So I have only 2 colors. And I need to color every point on the line. Every point on the line is an initial guess for me. Which roots do you think these points are going to go to? If I chose here, do you think it's going to be blue or red? What root do you think it's going to converge to?
1.
The 1, the blue root. What about here? What about here? What about there? What about here? Okay, so somebody give me a rule to determine blue versus red. We're going to solve the political problems of today.
Greater than 0 converge to blue, less than 0 converge to red.
Okay, so your guess is correct, but you haven't told me what happens at 0. You said if it's greater than 0, it goes to blue. If it's less than 0, it goes to -1, and you're not going to touch 0.
Well, it'll be purple.
Good. It will be purple. This will be the battle. I like the idea of having this as the battleground starting guess. Should 0 be converging to the -1, or should it be converging to 1? Or neither. I don't want to have anything to do with you guys until you can play nice. If I put in 0, I would have 1/2 of 0 plus 1 over 0. Yeah, you are not allowed to divide by 0. All right, so your guess is correct. All right, let's make it a little bit more interesting. I had in the title from C to shining sea. C is the complex numbers. So it's all numbers in the form x plus iy, where I either is or am the square root of -1, and x and y are real numbers. And so I'm now going to look at the polynomial x cubed minus 1 equals 0. I chose this very deliberately because I know if I take x equals 1, that's a root. How many of you remember polynomial long division? Or at least remember that at some point in your algebra classes you saw polynomial long division?
Yes.
Okay. If you don't, you can just multiply these polynomials together and check and see that it gives you x cubed minus 1. How can we find the roots of this? We can just use the quadratic formula. I know you really wanted to do the quadratic formula. I apologize for doing it in advance. And so when you go through and the dust settles, here are the 3 roots. X equals 1, x equals -1 plus I squared root of 3 over 2, x equals -1 minus I squared root of 3 over 2. So I'm going to plot these on the complex plane. Here's the root at 1, and I colored it blue. Here's the root at -1/2 I squared root of 3 over 2. I colored that red. And then the third party should be the green party. And I put it down there. All right? We're going to play the same game. I now am going to apply Newton's method, and I'm going to choose different points to be my initial guess. And I'm going to keep applying this. And I'm going to try to see what root does it converge to. Hopefully some of you are beginning to see why this is going to connect to the weather. If not, I will hopefully make that clearer in a moment. Can anybody give me a rule to figure out which root I go to? Or what do you think would be a wonderful rule if it was true? How many of you remember your rules of differentiation from calculus? Like the quotient rule? If you have the derivative of f over g, it's f prime g minus fg prime divided by g squared. If you could control the universe, you would probably have the quotient rule is f prime over g prime. Let's just make it simple. right? Derivative of a quotient, quotient of the derivatives. Derivative of a product, product of the derivatives. No. If you could choose a rule, how would you choose to determine, I give you a starting seed, how do you think I should determine where I go to? How would you generalize what we had a few moments ago? What would be the generalization? Yes?
For like the data and the root data, I would want x and y to both be positive.
So if they're both positive, I would go to the positive root?
Yeah.
Even if I'm over here. Ooh, yeah. So what do you think might be the rule to determine?
Well, you have to know what the maximum or minimum is.
Maximum, minimum what?
The value of the function. Or like of the, where it curves, basically.
So there's a nice simple way to choose.
The real number, maximum, minimum. Because otherwise they would go to infinity on the other side.
Right.
The half of the line in between.
Okay, the half of the line in between. So basically, like over here, draw a line.
No, between the points.
Oh, between the points. So if I'm trying to determine, if I'm over here, do we agree? If I'm over here, it should either be red or green. Do we agree? The blue should be out of the picture.
Yes.
Do you think this should be green or red? Tell me when it becomes red. So at what point do you think it becomes red? When it's halfway between red and green, you should be indifferent. And then if you're closer to red, you should go to red. And then what if you're halfway in between? What should you do? Neither, right? So is this a reasonable, and this is going back to the purple, okay? All these points here are closer to the blue and should go to the blue. These points are closer to the red. These points are closer. And hopefully I drew it correctly. I might have drawn it wrong, but I think I drew the wrong angle here. I think this angle should be a little bit steeper. Sorry, I apologize. But it should be basically whichever root you're closest to, that's the one you go to. All right? So what we do is we now have the computer calculate for each starting value what should we converge to. And you get the following shape. Is it somewhat reasonable? Is there at least parts of this plot that look good? It's cool watching the projector change colors. It's like the Wizard of Oz. Are there any parts of this that look good? Yeah, which parts look good? Yeah, this big stuff near here is going where we expect. This stuff near here is going where we expect. This stuff here is going where we expect. And the stuff near the purple boundaries, oh my. And if you look at the center, the computer is basically saying, I give up. The calculation is getting really, really bad. So I have a movie hopefully loaded up on this one. No. They often have really bad, cheesy music. I have put it on mute. And so you can hopefully see it zooming in. And so this is an example of a fractal. This is very similar to what we saw earlier today. That as you zoom in, you have the same rich structure again and again and again. And what is remarkable is minute differences in the initial condition lead to wildly different behavior in terms of where it ends up. If I move by like 10 to the negative 15, that changes which root I go to. So when I iterate, at the end of the day, these roots are well separated. And when I iterate, I'm very far apart from them. Okay. So this is the study of fractals and chaos. So you can't give a talk like this without mentioning the Mandelbrot set. If you do not mention the Mandelbrot set, you get into trouble. So the Mandelbrot set is defined as follows. Consider a complex number, and I can write it as x plus I times y. X and y are real numbers. And what I'm going to do is that I'm going to define a function as follows. You give me any input, I square the input, and then I add c. So I start at 0, and so I just get back to c. Then I would put in that value, and I would get c squared plus c. Then I would put in this value, and I get c squared plus c squared plus c. And I keep iterating. So at every moment in time, my next step is the iteration of my function applied to where I just was. And the Mandelbrot set is defined as follows. all the starting values that when I iterate, I stay bounded, that I color black, and that'll be the Mandelbrot set. And all the points that go off to infinity, I will color them. And I'll color them with different colors depending on how rapidly they go off to infinity. So here is an example of the Mandelbrot set. So all of this stuff over here, when I keep iterating, it stays bounded. And as I go further and further out, I start getting to places where interesting behavior happens. So I'm zooming in over here. If you look at this, this kind of looks like another copy of this set. And when I zoom in, there it is. And if you look over here and there, those look like other smaller copies of the set. I love pictures like this where, here's the set. I'm going to zoom in on the small part over here, and then this whole thing becomes this square. Then I zoom in on this part over here. Here's another copy of the set. I zoom in over here. Here's another copy of the set. Here is an extreme zoom at one place. And so it's worth just seeing. I mean, this video is 1 hour, 10 minutes, so we're probably not going to have enough time to see all of it. But it's just worth seeing, as you zoom in, just the fact that the incredible structure and the richness, and that you just keep seeing the same thing again and again and again.
Make a great screensaver.
Oh, they're wonderful screensavers. The patterns you get in these are absolutely incredible. So the slides have links to a bunch of these, and you can see over here there's a Mandelbrot set, but whoever was writing the program didn't want to zoom in on that. They decided to zoom in on something else, and so I'll go to this one. I think this one was a nice one. Yeah, this one's only 16 minutes. Yeah. And so now this one is trying to zoom in right at an interesting point, and you can see all those little leaves, and you'll see these spirals. Does this look like anything you've seen in the sea? And so we were talking about the turbulent 60s and whatnot. This is a different part of the 60s. But as you zoom in, it's this infinite spiral coming inward and inward and inward, like galaxies and whatnot. And it's absolutely amazing that as you keep zooming in, you keep seeing the same thing deeper and deeper and deeper. So here, I'll just go back out a little bit. And then you see that there's this little black dot in the center, and we'll just zoom in on that. And you can begin to see, there's another Mandelbrot set, which means you have the entire pattern beginning again. So it's this level of complexity that keeps going again. And there we talked about that little dot further up. There it is again. All right, so we'll stop that. Okay. So why do we care about stuff like this? So if such small changes can lead to wildly different behavior, what happens when we try to solve equations that govern things in the real world? I'm just trying to find what root do I converge to. And so the first paper that I mentioned, this is from Wikipedia, fountain of all knowledge, source of all wisdom. Okay. I still remember where I was the day I learned about Wikipedia and Google. But so Edward Lorenz developed a series of equations to try to model a very simple weather system. And what he noticed was chaotic behavior. And the way he noticed this was, he had run some things and something looked interesting. So he decided to just jump to that part the next day and just start the program from that point. So he had his printout, and instead of starting in the very beginning, he just told the computer, start here. But the printout was only printing out 3 digits accuracy, but the computer internally, I think, was keeping 6 digits of accuracy as it was doing the calculations. And when he ran it, he saw very quickly very different behavior from what he had in the printouts. He goes, wait a minute, it's the same, it's a deterministic equation. Each step determines what happens next. I should get the same result. And then what he eventually discovered is it was very sensitive to the initial conditions. And so small changes in the initial conditions very quickly led to rapidly different behavior. There are a lot of things in life where small changes will not lead to rapidly different behavior in short amounts of time. My son is a pitcher. If you release the ball here or here, you should not really be able to see the difference in my hand. It shouldn't have that much of an impact on where the ball lands. One should not go into the catcher's glove, and the other should not go to the second baseman. That's essentially what we're having here. very small changes lead in very short time to different behavior. So the next picture, also from Wikipedia, is looking at two different paths, one in blue, the other in yellow, and just very quickly they end up having very different behavior as to where they are. So just to end with a few takeaways, three things I want you to get from this. Math is applicable. The reason you take these calculus classes, the reason you take these other classes, is to have tools to try to apply to things in the real world. This leads to mathematical modeling. Ideally, you can use the same math to describe very different systems. If you've taken physics, you see that there's a lot in common between gravity and electricity and magnetism. They're both 1 over r squared forces. So the solutions to one set of equations will be the solutions to another set of equations. You can often see very similar behavior in very different systems. But the one that's the most important for a lot of the stuff you're doing, which is why you guys are doing the harder math than I am, is you are in a situation often when you're dealing with the environment of extreme sensitivity to initial conditions. You do not have the funding nor the technology to measure things to 100 digits accuracy or to computationally work with something with that much accuracy in a reasonable amount of time. So when you're trying to predict what's going to happen, a lot of people have basically interpreted this as saying that long-term weather forecasting is not going to be possible. You can have arguments as to how many days in advance can you do this. And so I have access to some good high-powered computing. I was talking with people here about 18 months in advance about this date because I was trying to arrange to come here on a very nice sunny day, good fall temperature, not cold like winter. And so this is about the limit as to what we can do, about 18 months. So thank you.